Today we're looking at section 4.3, day 3. We're still finding points of inflection. We're still using the second derivative test to use locate extrema. But today we're going to focus on particle motion. And given a position function, we're asked to find the velocity and acceleration. We've done that before. And we're asked to describe the motion of the particle. We've also been asked to do that before. But this time we're going to use our derivative test. This is page 215, number 28. Okay, so let's start by finding our velocity and our acceleration functions. And we just do that by taking the first derivative and the second derivative. 6t minus 6t squared. And if we take the derivative again, we get 6 minus 12 t's. Our problem tells us we just want the motion from t equals 0 to infinity. So what we're going to do is set our velocity equal to 0 and calculate what we get. So I think we can factor out a 6t here. 1 minus t. 6t, is that correct? I think so. So we set 6t equal to 0, and we get a 0. And 1 minus t equal to 0, and we get t is 1. So we're just going to have a critical point at t equals 1 and t equals 0, but we're using that as our endpoint anyway. So at those 2 points, velocity is 0, therefore our particle is stopped. Okay, it's stopped at t equals 0 and at t equals 1. And from 1, we're just going to go to infinity because I don't think we have any more critical points. There's no place where the derivative is 0. There's no right end point. So we stop at t equals 0 and stop at t equals 1. Now, between 0 and 1, let's look at the sign of our derivative, which is 6t, 1 minus t. All right, if we put a big positive number in there, we get a negative. If we put our little positive number in there, we still have a positive. All right, so that means this is an increasing function or moving forward. So at t equals 0, we're stopped. Then our particle moves forward. Our particle stops when the time is 1, and then it moves backwards from now until infinity. Okay, so that is basically describing the motion of our particle, and you could actually write that in words. The next problem is looking at a graph. This is number 30 on page 215. Given the graph of the position, so this is position. Be careful about that. And I like to call it S. Sometimes your book calls it X. I like to call it S. S, V, and A. But anyway, it says find where the velocity equals 0. Okay, so this is a position graph. So anytime that, let's see, velocity equals 0. Velocity equals 0 whenever we have a maximum or minimum, right? So we might count one down here. It's a different color. We might count one down here. There's where velocity is 0. Up here, we have v equals 0. And down here, we have v equals 0. This one over here at 16 doesn't go far enough to let us know. All right, so this is like t equals 4 and 12. And we'll call it -1 also. 4 and 12. Okay, so -1, 4, and 12. And when is acceleration equal to 0? Okay, so remember that acceleration is the second derivative. The second derivative means that when it's equal to 0, we have a point of inflection. When the acceleration equals 0, that means concavity changes. So in this book, in this graph, we are going to look at where does the concavity change. Okay, here we have concave up until about right here, and then we have concave down until about right here. Then we have concave up until about right here, and then we have concave down until about right here, and then we have concave up, and then concave down. Those are our 1, 2, 3, 4, 5 places where the acceleration is 0. Okay? Emphasize those just a little bit more. And I'm just estimating where the graph changes from concave up to concave down. All right, so those places are at t equals 1.5, 5, 7, 10, and 14. All right, so there are our answers for where does concavity changes. And that's that problem. Okay, next. This is in your assignment, I think, page 216, number 42. I made this cute little graph, but I don't think I'm going to use it. I think I'm going to draw right on here. Hopefully you can see that. Look in your book on page 216 if you can't really see this graph very well. I took a picture of it. But anyway, graph of the first and the second derivative is shown. Add a sketch of a possible graph that includes the point P. Let's evaluate this graph first. We're going to draw another graph right on here that starts with point P and goes somewhere. All right, so let's take a look at this graph, and let's look at the blue one first. That's the first derivative. Remember, when the first derivative is equal to 0, this is a max or a min. Down here, we have a decreasing function. Decreasing function from 0 to the max. Wait, this is decreasing. Actually, this is a min. It's a max or a min. It happens to be a min. I'll tell you why in a second. This is decreasing, and then up here is increasing. It's above the line. Okay, so we have a positive first derivative. We have a negative first derivative. We're just looking at the blue graph. Right here we have an extrema. The reason we know it's a min is because our graph is decreasing, then increasing. So we must have a minimum at this point. All right, so that's what it tells us. Right here, our graph goes down, then goes up. All right, so let's look at the red graph, which tells us the concavity. Okay, so first derivative tells us extrema, and it tells us increasing and decreasing functions. Okay, the second derivative is going to tell us concavity. And anywhere that f double prime equals 0 means that it changes concavity. Okay? Concavity changes. All right, so I'm going to move this whole thing down. Key. This and this. Okay, so second derivative is the red line. So we know right here it's 0, and right here it's 0. That means we're changing concavity. This down here is a below the line negative concavity, which means it's concave down from here to here. From here to here, it's concave up. And from here on, it's concave down because the graph is below the line. Okay, concave up, concave down, concave up, concave down. All right, so concave down. This is decreasing all the way to here and concave down right until right here. So this goes like this, concave down. When it gets to this point, and it doesn't have to be right there, it could be right here, then it starts concave up. Okay, concave up. Down here, we're going to have a minimum. And our graph goes from decreasing to increasing. So we're going to increase up to the, and be concave up all the way between here, these 2 points. I hope you can see my points. And then we start to be concave down, but we're still increasing because we're above the line, okay? So this green line magnifies our graph. From here to here, it's decreasing and concave down. From here to here, it's decreasing and concave up. From here to here, it's increasing and concave up. And from here to here, it's concave down and increasing. Okay, that was fun. Now we have another one on page 217, number 47. Okay, so I love this problem because it helps you understand things about graphing. This is number 47, and 47, 48, 51, 52, they're all about evaluating graphs or creating a graph and finding extrema, et cetera, et cetera. Anyway, let's start with number 47 and see what it gives you. I always plot what I know, okay? So this problem gives me 3 points. It says function at -2 equals 8. It says the function at 0 equals 4, and the function at 2 equals 0. Those are 3 points. Graph them. -2, 8, there's a point. 0, 4, there's a point. And 2, 0. 3 points. Okay, we're off. Okay, well, let's look at what the rest of this tells us. So now we've graphed these 3 points. The next thing tells us that the derivative at 2, the derivative at -2 are both 0. That means this is an extrema and this is an extrema, or a critical point, right? It doesn't tell us it's necessarily an extrema. It'll be depending on whether it's increasing or decreasing on both sides of that. So the next 2 statements, this one and this one, tell us about whether the function is decreasing or increasing. So the derivative is greater than 0. It's increasing for x greater than 2, absolute value of x greater than 2. So over here, it's increasing, and over here, it's increasing. And that means that the other statement is just the opposite. It's decreasing for x less than 2. So in between here, the function is decreasing. So that means it's going up, then it's coming down, and then it is going up. Okay, now that's a possible graph right there. But we have to take in the rest of the story. Okay, so hold on to your horses for just a second while we also check this second derivative, which is concavity. X less than 0, the derivative is less than 0. This means it's concave down for x less than 0. X greater than 0, it's concave up. So, x less, concave down, and this way is concave up. All right, with all this stuff, I can draw this beautiful, lovely, wonderful graph. It's increasing to right here, and then decreasing. That means this is going to be a max. And then it's decreasing and increasing. This is going to be a min. So my possible graph drawing wasn't bad, was it? Right here is a point of inflection. The derivative, it doesn't really say what happens here at 0, does it? But we do know that it changes concavity. So this is all concave down, and this is all concave, oops, I went too far, concave up, and this is a minimum right here, the green dot. Okay, so notice concave up on the left, concave down on the right. That is graphing. And that is the end of section 4.3, finally.